Okay, so ladies and gentlemen, all along we've come to understand the classical Malmquist. The classical Malmquist is the one that was postulated by Fair, Groskop, Lindgren, and Roos in a two-factor, and then extended by them to variable retention scale by Fair, Groskop, Norris, and Zahn in a three-factor. Now, when you normally estimate these two Malmquist indices, the index can be split into two. What are they? The index can change part is what is known as catching up to the frontier. It's a movement along the frontier. It is a movement along the frontier. It is how far you are from your previous frontier. So it is a reflection of managerial efficiency change or managerial performance. Then there is another part which is known as a frontier shift, the technological change part. This has gone in the industry and we've looked at that. It has a problem or some problems. One of them is that it's not able to estimate linear programming infeasibilities. It's not able to estimate well mixed period, efficiency scores, because sometimes some of the mixed period, super efficient mixed period efficiency scores become infeasible. So the biennial, which we have already done, corrected that problem. The biennial required just two frontiers, two time frontiers, just like the classical, but two. That's why it's called biennial. There is another frontier, which is called the global frontier, which does not combine two frontiers, but it combines all the frontiers, whether it's 10 or 100 or million, all the frontiers, taking the extreme guys. That frontier is known as the global frontier by Pastor and Lovell. The biennial frontier is by Pastor et al. 2011. The global frontier is Pastor and Lovell 2005. And that global frontier also solves infeasibility. Let's go back to the classical. The technological change portion of the classical Malmquist, or the frontier shade, it is calculated for each individual. So each individual DMU, its technological change, which you all know. So DMU A will calculate its efficiency change and the technological change. DMU B will calculate efficiency change and technological change. And DMU Z is calculated efficiency and technological change. So it is for each individual. But Asmild and Tam in 2007 were able to prove that even though it is calculated for individual firms, eventually, because the researcher wants to make conclusion about the industry as a whole, they normally would take the arithmetic mean of this score or the geometric mean of the score, and then they will have an average score for all the firms in the industry. So these scores are aggregated. So the local technological change becomes more or less like a global technological change, is to develop a proper approach, a simple approach, of course. That is called the global frontier shift, or what you might call the global technological change, which we know as a component of the global Malmquist. Now, why global? So in other words, the moment you have that thing in mind, you are not even concluding about individual firms anymore. Everything you say, everything you see is all about the industry, the entire DMUs instead of individual. And all the advantages of that relative to the classical change. So the first thing is that when the data set is sparsely populated, and when the frontiers change shape over time. When I say frontiers change shape over time, if you draw a particular frontier, okay, particular frontier, production possibility frontier, and you draw another one, they can be parallel. And because they are parallel to each other, there's more or less like there's no change, because the change will be constant between the two frontiers. This is said to be Higgs neutrality. Higgs neutrality. But in real life, the frontiers are not parallel, they are intersecting. So year 1 frontier can intersect year 2, 3, 4, 5, year 14 frontier. And so what it makes is that it makes it look like the frontiers are changing shapes over time. And when you have a situation where there are a lot of changes over time like that, the global frontier shift is very important because it captures those shifts. And of course, when they change shape over time, the data set for year 1 will be different, significantly different from the data set for another year. The global frontier shift helps to see those patterns, those situations. Number 2, you don't need information about separate DMUs. You don't need to know whether a particular DMU, is different. For example, this DMU is different from that DMU. You don't need that information because it's all put together in the estimation process. You don't require direct information about them. Because whatever, let's say that you are trying to know how the Ghanaian banking industry looks like. You don't need any particular information about stand chart, because stand chart is inside the Ghanaian banking industry. So whatever it has, it will be captured. It is inside the industry, and you are capturing the industry. So whatever thing you get from the industry, and stand chart is contributing to it. You should reflect in whatever you will get from it. Okay, so you don't need separate information. Number 3, you are going to see that the way you calculate the global frontier shift, it gives you a better estimation of the total patterns. Okay, the pattern. Sometimes there are trends and patterns. You are able to get the complete pattern because of the manner in which estimation is done. Number 4, you can use the global frontier shift, okay, to estimate not only time differences, not only difference between time period 1 and time period 2, to check which period is better, or to check whether the firm improved between the 2 time periods. It's not only when you're dealing with time period, but even when you're dealing with groups. So you want to compare foreign against domestic, or you want to compare AMU versus ECOWAS versus SADC versus ICA versus ECAS. So you want to know the differences between these things. The global frontier shift gives a better estimation. And the way it does that is also different from the meta frontier by O'Donnell, 2008. So that's a 4th point. Point number 5 is that even if the data is unbalanced, and coming back to you, Prince, your point, even if the data is unbalanced, all the information about those that are causing the unbalancedness are incorporated. So the data is unbalanced. Maybe you are just checking the difference between time period 1 and time period 14. But time period, 15 has some more data than 1 and 14. But that information, that extra DMUs that make the data unbalanced, they will carry information that will help you in your estimation process. And because of that, your estimation will be encapsulated because it takes into consideration all of, even if you're not going to, you're not going to be able to estimate, productivity measures for those unbalanced information, unbalanced DMs. And finally, number 6, is easy to calculate. The global frontier shift is easy to calculate. It's just 3 steps. And we shall look at that. So those are some of the merits of the global frontier that warrant the use of it. Okay. Now, let's formalize it and give you the 3 steps in calculating the global frontier. So let's assume that we have JDMUs, J capital J DMUs, and each one of them is a small j. So you have J producers, JGM. They are all operating over time period T, small t, equal to 1 all the way to capital T. Now, it is also possible, note it, I said they are all, which means it's also possible that some of them may not be in all the time periods. In other words, it's possible that the data will not be balanced. So take note of that. Each of them is using M inputs. M is the total number of inputs. The inputs for each DMU J is X, and X is a member of real positive terms of inputs. The same thing is for the outputs. Those inputs are being used to produce S outputs. So the total number of outputs are S. That you have. So you have outputs R starting from 1 to S. And then you can put all the inputs together and create an input matrix, capital X, and an output matrix, capital Y. And you can create an input vector, X bar, and an output vector, Y bar. So on the basis of this, how do you calculate the global frontier shift, the technological change version, the global technological change? The first thing you want to do is to calculate the distances of all the DMUs in all time periods, all the DMUs in a particular time, but also in all time periods. That's all the DMUs are capital J. In all time periods are capital T. You measure the efficiency of all of them relative to each time period's frontier. So let's assume that the time periods are 1 and 2. Or let me put it. Let's assume that the time periods are 1 and 5. Okay. We are going to deal with time periods 1 and time period 5. And all the DMU, the number of time periods are 10. And the number of DMUs in time period 1 are different from those in 2 and those in 3 and those in 5, all the way up to those in 10. In other words, some firms enter, some leave, some enter every year. So the data is unbalanced actually. What you do is that you calculate the efficiency of all the firms. Okay? So let's say that when you count all the observations, they are about 500. You calculate all the efficiency of all the 500, but relative to only time year 1. So not relative to the global, like the global Malmquist of Pastor and Lovell, but relative to only year 1. So relative to only year 1, each firm is going to have a score. So you're going to have all the 500 firms having a score. What score? But the scores will be different depending on where that particular firm is located relative to the frontier. Some of them will be, just a second, let me pause this thing.